Maria-Angela Franceschini, associate professor at Harvard Medical School and optical engineer and neuroscientist at the Martinez Center. Mari.
Okay, thank you, Bruce. I would like to use my time today to discuss the role of FNIRS, functional near-infrared spectroscopy, in human neuroscience, the challenges of this methodology, and how we can best address them. Okay, so functional near-infrared spectroscopy uses light to interrogate the human brain. Okay, I'll stay here. And the light is diffused because of the eye scattering when it enters the body, is absorbed by hemoglobin, and loses coherence due to the moving red blood cell. All this changes heal information about the blood volume, cerebral blood flow, and cerebral oxygen consumption. And actually, there are a large number of biomarkers behind just oxygen, the oxyhemoglobin concentration. So with advanced NIRS, we can measure cerebral blood flow or cerebral metabolic rate of oxygen that are important for better understanding human brain function. And because of these and other important properties, FNIRS has established itself as a complementary and useful neuroimaging modality. And, oh yeah, I have to press this one. As a demonstration of that is the increasing number of publications over the years. It started 25 years ago with a few papers about technology development and feasibility study, and thanks to the large user adoption, the number of publications has grown a lot. And this user adoption has been also supported by the establishment of the Functional Near-Infrared Spectroscopy Society that was funded to facilitate interaction between user and developers. And this society is user member-driven and has a very active Facebook group. So I took advantage in preparing this talk of the Facebook group and posted some polls to have a broad, to make sure I give a broad overview of the field. My first poll was about what are the biggest opportunities with this technology. And as expected, the big advantage of FNIRS is easy to use and the ability to use it in ecologically valid settings. So there is a long number of studies like hyperscanning, brain-computer interface, neurofeedback, or FNIRS in developing countries that can be done thanks to this technology, and they're not easily done with other modalities like fMRI. Just to give you an example of studies happening now, with FNIRS we can do studies while people walk around campus or drive cars or play music in synchrony. And another big opportunity for FNIRS is studying brain development. So again, it's well suited for infant study because of the child-friendly environment of the method, but also technically speaking, is because of the thin skull and the small head of children. We get this technology is very good on kids because we can reach deeper into the brain and have a stronger signal. The technology has more trouble when we go in adult population where the distance between the brain and the scalp is larger. And we'll address this later. But with respect to children's studies, actually probably the majority of the FNIRS studies are in children. And this is in net contrast with the other imaging modalities. Then another important opportunity for me is clinical neuromonitoring. So there is, because of the various biomarkers, not just cerebral oximetry, but also blood flow and CMRO2, there is a wide range of clinical application that FNIRS is useful for, and is aiming to individualized care. So, as an example, these are ongoing clinical studies in my lab. Oops, the movie is not starting, but that's okay. So we go from premature infants monitoring on cerebral perfusion to studies in African children and OR measurements both in adults and infants and neuromonitoring. So then I asked what are the major limitations, and the limited depth sensitivity is the biggest limitation for NIRS. So essentially when we inject photons, the majority of these photons that reach the detector only travel in the superficial scalp, extracerebral area, and only a small amount, a small fraction is seen in the brain. And so in adult with CW NIRS with simple system, the sensitivity to brain is only 10-15%. And this is a real issue, especially for clinical application. We want to isolate the brain signal from the scalp confounding signals. And another limitations that come up with my polls that I didn't really think about is the lack of unified data analysis. So while engineering provide us a lot of toolboxes to analyze the data, the users feel the needs to have some guidance. So the society recognize this problem, and we have established a standardization committee, is just forming now, that is working on providing this guideline of unified data analysis. And while I told you FNIRS can be used to study people during movement, if you want to use advanced system, high-performance systems, these are still fiber-based, and there are all the complications with the arrangement with a lot of fiber in the head. So, and this, when then I ask is the technology solution that you will invest on, this is actually the first thing, it's very important to be really, if you really want to achieve this ability to study the brain while the person is moving, it's very important to have a robust system and not lose any of the advantage of the high-performing system while we do the experiments. So while there is a lot of commercial devices, and there is a lot of research groups that are developing fiberless systems, there is a lot to do here, especially for the advanced NIRS. So, and one other point that also the previous speaker raised, for the advanced NIRS, there is few labs that have this system, but because of the high cost, there is a limited spread of these devices. And especially if we go then to gated system and time resolve systems that are very expensive currently. And why we want these devices, just to give you an example, with time resolves NIRS, essentially we can isolate the photon that have traveled deeply with respect to the superficial one by just detecting this fraction, opening the gate of the detector at this time only. And what this does, he increases the sensitivity to brain, kind of double it. And if you look here, it double it also if you have a short source detector separation. And what does it mean? It means that now you get more light, because the light doesn't need to go down here, it just goes down and back up, and also improve lateral resolution. And And then he allow you to have in the single optode a co-localized source and detector, and this will make it much simpler, the construction of probes and such. This can also be achieved using a high-density system, maybe interferometric NIRS. For sure, it can be achieved by tagging the photons, so like with ultrasound, with acoustic method. And so to bring all these new advanced methods that will improve a lot the contrast for NIRS and will open up opportunity to older population, not just children, it's important that specific components, semiconductor, detector, or sources are built. And these are very ad hoc. It's not something that you can find commercially. So, to recap, I told you that because of the property of FNIRS, we have several opportunities here that we can address, like very important among them, the ability to do experiments and understand how the brain works in a naturalistic setting. The fact that we can acquire several biomarkers like oxygen metabolism. And there are several limitations that can be addressed with advanced system or improved technology. And then to spread to users, to have more people giving this tool to more people, we have to reduce the cost and maybe make the system also portable and wireless. So what is needed for the technology to further advance is new sensor, new light sources, and new algorithms to have stronger reconstruction, and a lot of specialized electronics. And I think that's all.
Thanks very much. Thank you so much for keeping on time.
Thank you.
Perfect. A question from the panel to start?